At 2:46 p.m. on March 11, 2011, a magnitude 9.0 earthquake struck off the coast of Japan. What followed was a wall of water, 15 meters high, moving at 700 kilometers per hour toward 400 kilometers of populated coastline. It killed 20,000 people in under an hour. Japan's response was to build the largest wall ever constructed in human history. At 2:46 p.m. Japan Standard Time, the Earth convulsed beneath the Pacific. Instruments registered a magnitude 9.0 rupture, the strongest ever recorded in Japan, and among the 5 most powerful globally. In a matter of minutes, the seabed shifted, displacing an immense column of water. The resulting tsunami raced across open ocean at speeds near 700 kilometers per hour. Along the Tohoku coast, waves reached heights of 15 meters, with some local surges even greater. Within 30 minutes, the sea invaded nearly 400 kilometers of shoreline, overwhelming towns, ports, and farmland. The human toll was staggering. Official figures from the National Police Agency list 19,759 confirmed dead, over 6,100 injured, and more than 2,500 still missing. The vast majority of lives were lost to the tsunami itself, not the quake. Entire neighborhoods vanished in minutes. In the hardest-hit prefectures, Iwate, Miyagi, Fukushima, families were swept away and communities erased from the map. The disaster left 123,000 homes destroyed, with millions more damaged or without basic services. The economic losses reached $235 billion, nearly 4% of Japan's gross domestic product. The World Bank labeled it the costliest natural disaster in history. The destruction extended to critical infrastructure, including the Fukushima Daiichi nuclear plant, where a 15-meter wave breached defenses, triggering cascading failures, and a nuclear crisis that forced more than 100,000 people to evacuate. What remains are not just numbers, but the absence of thousands, lives interrupted, families separated, towns forever changed. This was not a distant tragedy. It was a national trauma that exposed the limits of existing defenses and demanded a response on a scale never before attempted. Within months of the disaster, Japan's central government authorized what would become one of the largest civil engineering projects in its history. Cabinet papers and budget records reveal a commitment of $12 billion to construct a continuous tsunami wall, stretching approximately 400 kilometers along the Tohoku coastline. The project was divided into 440 separate sections, each tailored to the irregular bays, headlands, and river mouths that define the region's geography. Construction began in 2012 with a target for substantial completion by 2022, a 10-year window to reshape the shoreline and, in theory, shield it from future devastation. The Reconstruction Agency, established in early 2012, coordinated the massive effort, working in tandem with the Ministry of Land, Infrastructure, Transport, and Tourism. Their mandate was clear: prevent a repeat of the catastrophic losses of 2011 by building a barrier that could withstand waves as high as those that breached every existing defense. The scope was unprecedented, not only in length, but in its ambition to create a nearly unbroken line of protection across 4 prefectures. Decisions were made at the highest levels: the special reconstruction budget, drawn from a broader 19 trillion yen national rebuilding fund, ring-fenced resources for the wall's design, procurement, and construction. Each section required local adaptation, but the central agencies maintained strict oversight, using GIS mapping and standardized engineering criteria to ensure that no community would be left exposed by a gap in the barrier. This was more than an infrastructure project. It was a national statement, an attempt to translate collective grief and fear into concrete, steel, and stone. The wall's scale and cost reflected the magnitude of what Japan had lost, and the determination to never face such loss again. Yet even as the first foundations were poured, questions lingered about the limits of what any wall could promise. Under the surface, every segment of Japan's tsunami wall begins with a hidden line of steel. Contractors drove continuous sheet piles 10 to 15 meters below the seabed, forming an underground barrier that anchors the structure against the relentless force of water. These steel sheets, often H-beam sections with 30-millimeter thickness, are welded and locked together, creating a watertight core designed to resist both uplift and undercutting, failures that had doomed earlier walls. Above this foundation rises the superstructure, high-density reinforced concrete poured in modular panels. Each section targets a compressive strength of at least 45 megapascals, with additives like silica fume and polypropylene fibers to absorb shock and reduce cracking under repeated wave impact. Engineers specify grade B 500 rebar, coated in zinc to guard against the corrosive salt air and spray. The goal is a wall that will endure decades of battering without losing integrity. The wall is not a single uniform barrier. Instead, it's a mosaic, 440 distinct segments, each mapped to the unique contours of the Tohoku coastline. Some rise to 15 meters, matching the height of the Fudai floodgate that saved an entire village in 2011. Others step down to accommodate river mouths or harbors, always recalibrated to local risk. Design drawings show how each piece fits into the larger line, with contractors adapting formwork and pouring schedules to the irregular rhythm of bays, inlets, and headlands. The sheer volume of concrete and steel required convoys of trucks, round-the-clock pours, and a choreography of cranes and laborers working in all weather. Beneath the visible surface, the wall's strength lies in its buried foundation and the relentless attention to detail that defines every meter of its construction. Beyond the concrete superstructure, the wall's outermost defenses rely on a layer of armor designed to blunt the force of the sea itself. Engineers specified the placement of approximately 48,000 tetrapod units, four-legged concrete forms, each weighing around 2 tons, along the seaward face of the barrier. Manufactured by firms such as Kawasaki Steel and transported to coastal staging areas, these interlocking shapes break up incoming waves, scattering their energy before they strike the wall. Hydraulic cranes, guided by GPS, set each tetrapod in a precise pattern, forming a porous shield that slows the surge and reduces scouring at the base. The result is not a smooth rampart, but a jagged, engineered reef, built to absorb the relentless battering of the Pacific. Where rivers meet the ocean, a different challenge arises. Tsunami waves push seawater far upstream, but after the surge recedes, floodwaters trapped behind the wall threaten to inundate low-lying land. To address this, engineers installed automatic floodgates at major river mouths, including Kitakami, Naruse, and Tono, integrating seismic sensors that detect ground motion above 0.2 G. When a major earthquake strikes, the system triggers the gates to close in under 5 seconds, sealing off the river's mouth before the tsunami arrives. These gates, supplied by Toyo Engineering and Kawasaki Heavy Industries, are tested under simulated magnitude 9.0 shaking to ensure faultless operation even during power outages. The aim is to create a seamless line of defense, one that can adapt in real time to the unpredictable sequence of earthquake and wave, and buy precious moments for evacuation. Yet for all their technical sophistication, these final layers of protection are visible reminders of the scale of loss that drove their creation. The armor and gates stand as both shield and symbol, evidence of a nation's determination to defend its people, and a constant question about whether any structure can truly hold back the sea. Engineers and policymakers defending the new seawall point to one simple metric: time. Models from the Ministry of Land, Infrastructure, Transport, and Tourism show that a 15-meter barrier is expected to slow the inland rush of tsunami water by 1 to 2 minutes. In a disaster measured in seconds, this margin can mean the difference between life and death. The claim is not just theoretical. In Fudai, a small village on the Iwate coast, a 15-meter floodgate built decades earlier stood firm against the 2011 tsunami. While neighboring towns suffered devastating losses, Fudai recorded 0 deaths from the wave. Residents remember watching the water rise, batter the concrete, and finally recede, leaving the village intact. One former engineer recalls that they were told the gate would never be needed, but it saved the whole village. For planners, Fudai became a proof of concept, a rare instance where the right structure, built high enough, bought precious minutes for evacuation and preserved an entire community. No matter how imposing, every wall faces a question it cannot fully answer: what happens when the sea climbs higher? Computational fluid dynamics models from Tohoku University have tested the wall's limits. In controlled wave tank experiments, water overtopping a 15-meter barrier forms a violent hydraulic jump on the landward side, amplifying the force by up to 1.5 times compared to the initial wave. This surge can batter secondary defenses and overwhelmed drainage systems. The models also reveal that under certain conditions, run-up heights may exceed the wall by as much as 2 meters. These findings unsettle the idea of absolute safety. Engineers acknowledge that the wall's design is based on the 2011 event, but future tsunamis could be larger, longer, or arrive from unexpected angles. Policy debates now turn on this uncertainty. How much risk remains, and how much can be engineered away? For every meter of concrete, there is an open question about the next wave, one that numbers and blueprints cannot fully resolve. Today, concrete walls trace the scars of 2011, protecting lives but dividing communities and the sea. As climate risks rise and memories fade, Japan's gamble stands, monumental, imperfect, and deeply human. The next wave will test not just the wall but the faith placed in it.